A very good day to everyone. My name is Loin Chuan, and today our group will be presenting our assignment for MET 12203 Machine Learning titled Design, Development and Analysis of the Artificial Neural Network Model for Weather Condition Classification. This assignment was completed by myself, Muhammad Naim, and Muhammad Saleh. To begin, let me give a brief introduction to our project. Artificial intelligence and machine learning has become widely used across many engineering fields, from medical diagnosis to financial prediction and, of course, in our case, weather classification. One of the most well-known machine learning techniques is the artificial neural network (ANN). It's designed to mimic how the human brain works using layers of connected artificial neurons that learn patterns from data. The goal of our project is to use the ANN model to automatically classify weather conditions, specifically sunny, rainy, heavy rain, and cloudy, based on real historical weather data recorded over 5 years. The main issue we are addressing is that weather is influenced by several interrelated environmental factors, including temperature, humidity, rainfall, and wind speed. Traditionally, weather is classified manually using simple rule-based approaches. For example, if it rains heavily, we label it heavy rain. However, in reality, weather pattern can be complex and overlapping. For instance, high humidity does not always mean rain. It could be cloudy. This overlap made simple rule-based method unreliable. Therefore, we need an intelligent model that can automatically learn the non-linear relationship between all these meteorological features and produce accurate weather condition prediction. That is exactly what our ANN model is designed to do. We have 4 clear objectives. First, we prepare and pre-process the weather dataset by handling missing value, encoding categorical labels, normalizing feature, and splitting the dataset. Second, we develop 2 ANN models using the multi-layer perceptron architecture with different configuration of hidden layers, neurons, and fine-tuning technique. Third, we evaluate both models using multiple performance metrics. And fourth, we compare the 2 models and determine which one performs best. We selected a 5-year weather dataset stored in CSV format, which we uploaded to Google Drive and accessed through Google Colab. The dataset contained 1,826 daily weather records with 4 input features: temperature in Celsius, humidity percentage, rainfall in millimeters, and wind speed in kilometers per hour. The target variable is the condition column, which is categorical label representing the weather class. The data set also includes a date column, which we did not use directly as a training feature, but we noted it as a potential area for future feature engineering. Looking at the class distribution of our dataset, we can see that the 4 weather conditions are not equally represented. Sunny is the most common class with 894 records. That is about 49% of the total dataset. Rainy follow with 485 records. Heavy rain with 379 records. And cloudy is the minority class with only 68 records, which is about 4% of the data. This imbalance is noteworthy due to the limited sample. The ANN model may classify cloudy conditions with less accuracy compared to sunny conditions. To ensure fairness, we apply a proportional split so that each weather class is equally represented in both training and validation set. Before we dive into the code, let me briefly explain the software and tools we use for this project. Our development environment was Google Colab, a cloud-based Python notebook platform that supports GPU acceleration. It is ideal for training machine learning model without a powerful local computer. We wrote all our code in Python using pandas and NumPy for data loading and numerical operation. Scikit-learn for label encoding, feature scaling with standard scaler, and the train test split function. TensorFlow and Keras for building and training the ANN model, and Matplotlib and Seaborn for plotting our result, including accuracy and loss graph, confusion matrices, and predicted versus actual output graph. I will now hand over to Muhammad Naim for the detailed data pre-processing steps. Thank you.
Thank you, Luis. Assalamualaikum and hello everyone. I'm Muhammad Naim and I will cover the data processing, model development and training graph. Let me start with data processing. Before training any ANN model, we must clean and prepare the dataset. Step 1 was checking for missing value using this. Any missing value in numerical column, temperature, humidity, rainfall and wind will fill with the mean value of that column. The missing value in the condition column were replaced with the mode. Step 2 was labeling and coding. This condition column is text label, but ANNs can only process number. So we use the label encoder to convert cloudy to 0, heavy rain to 1, rainy to 2, and sunny to 3. Step 3 was one hot encoding. We applied to categorical to convert the encoded label into a categorical format, which is required for softmax activation function in the output layer. Step 4 was feature scaling using standard scaler. This normalized all input feature to have mean of 0 and standard deviation of 1. With this, feature with larger numerical range would unfairly dominate the training process. After pre-processing, we split the dataset into training and validation set. We use 70-30 split. 70% of the data, which is 1,278 samples, was used for training in the ANN. The remaining 30%, 448 samples, was used for validation. We also set a random state of 42 to ensure the split is reproducible. Every time we run the code, we get the same split. Importantly, we use the stratified parameter during the split. This ensures that the proportion of each weather class is maintained in both sets. Without stratification, the validation set might have very few or no cloudy samples, which would make evaluation unreliable. This 70-30 split directly satisfies the assignment requirement. Now let me explain our first ANN model. ANN model 1 is basically multi-layer perceptron with 2 hidden layers. The architecture is input layer with 4 features, followed by hidden layer 1 with 16 neurons using ReLU activation, then hidden layer 2 with 8 neurons using ReLU, and finally the output layer of 4 neurons, one for each weather class using softmax activation. ReLU was chosen because it is computationally efficient and handles non-linear classification well. Softmax is used in the output layer because it converts the raw score into class probabilities, which is required for multi-class classification. We trained this model for 100 epochs using the Adam optimizer and categorical cross function. The result, model 1 achieved a validation accuracy of 98.36%, a validation loss of 0.0385, with the best performance occurring at epoch 94. This is already a strong result, showing that even simple ANN architecture can classify weather conditions effectively. For ANN model 2, we designed a more complex and fine-tuned architecture. The architecture includes input layer, dense layer with 64 neurons, and ReLU activation, a dropout layer at rate 0.2, dense layer with 32 neurons, and ReLU, dense layer with 60 neurons, and ReLU, and finally, the output layer with softmax. We add 2 important fine-tuning techniques. First, dropout regulation at rate 0.2. We add 2 important fine-tuning techniques. First, dropout regulation at rate 0.2. This randomly deactivates 20% of neurons during each training step, which is prevent the model from over-relying on specific neuron and reduce overfittings. Second, early stopping with patient of 10. This monitors the validation loss and automatically stop training if there is no improvement for 10 conservative epochs. This prevents unnecessary training and saves the best model weights. The result, model 2 achieved a validation accuracy of 99.45%, a validation loss of 0.0198, and the best epoch was epoch 83. As you can see, model 2 outperformed model 1 in both accuracy and loss. Here is a direct side-by-side comparison of both models. The key difference are model 1 has 2 hidden layers with 60 and 8 neurons. Model 1 has no dropout and no early stopping. Model 2 uses both. Looking at the result, model 1 achieved 98.63 and loss of 0.0385 with best epoch at 94. Model 2 achieved 99.45% accuracy and loss of 0.0198 with the best epoch 83. Model 2 is clearly the best performing model. It achieved high accuracy and lower losses. A lower loss value is particularly important. It means Model 2 is not just accurate, but also more confident and stable at its prediction. The deeper architecture with dropout and early stopping allow Model 2 generalize better to unseen validation data. Now let me explain the evaluation metric we use in assess model performance. There are 6 metrics. One is a validation accuracies, the percentage of sample correctly classified in the validation set. The higher, the better. Model 1 is 98.36%. Model 2 is 99.45. Second is validation loss. The categorical cross entropy error between predict and actual output. The lower, the better. Model 1 is 0.0385, while Model 2 is 0.0198. Third is best epoch. The epoch number at which model achieved its best validation performance. Model 1 peaked at epoch 94, Model 2 at epoch 83. Classification report show precision, recall, and F1 score for each individual value class. Fifth is confusion matrix, a heat map showing which class the model confused with each other. This helps identify weak spot in classification. And lastly is predicted versus actual graph. A line plotting comparing the model predict class level against the true level across 50 validation samples. If the two lines closely overlap, the model is performing well. All of these 6 metrics satisfies the assignment evaluation requirement. This slide shows the training graph for both models, the accuracy graph and the losses graph for each. For accuracy graph, we plot the training accuracy and validation accuracy per epoch. A good model shows both lines increase together and converging. If training accuracy is much higher than validation accuracy, it indicates overfitting. For the loss graph, we plot training loss and validation loss per epoch. A good model shows both lines decreasing and stabilizing. If validation loss starts increasing while training, loss continues decreasing. That is a sign of overfittings. For model 1, the best accuracy was reached at epoch 94. For model 2, the best validation accuracy reached at epoch 83. The early stopping callback helped model 2 stop the optimal point. I will now hand over to Mr. Saleh, who will present the evaluation result, discussion, and conclusion. Thank you.
Thank you, Naim. Good morning, everyone. I am Muhammad Saleh and I will cover the evaluation result, including the confusion metric, predicted versus actual graph, result summary discussion, limitation, suggestion, and conclusion. Let us begin with the confusion metric. As confusion metric is a table that show how many samples were correctly and incorrectly classified for each value class. For model 1, looking at the metric, the diagonal cells, which represent correct prediction, are the darkest, showing that most samples were correctly classified. The off-diagonal cells show misclassification. For model 2, the confusion metric shows even fewer misclassification. This is consistent with the higher accuracy of 99.45. The most common confusion across both models is between rainy and heavy rain, because these two classes have very similar temperature, humidity, and rainfall value, making them harder to distinguish. Model 2 confusion metrics show tighter classification, especially for the minority cloud class. This slide shows the predicted output versus actual output graph for both models. In this graph, we take the first 50 samples from the validation set and plot two lines. The blue line represents the actual value class level. The orange line represents what model predicted. If the model is performing well, both lines should closely overlap. For model 1, you can see that the predicted line mostly follows the actual line, with a few deviations, consistent with its 98.36% accuracy. For model 2, the predicted line follows the actual line even more closely with noticeable fewer deviation, consistent with 99.45 accuracy. This graph visually confirms what the accuracy number already tells us. Model 2 is the better performing model with tighter, more accurate prediction. This graph satisfies the assignment requirement to plot predicted output versus actual output for both models. Let me now summarize the key results from both models side by side. ANN Model 1, architecture dense 16, dense 8, and then output. Validation accuracy 98.36. Validation loss 0.0385. Best epoch 94. No dropout, no early stopping. ANN Model 2, architecture dense 64. Dropout 0.2, dense 32, then 60, then output. Validation accuracy 99.45, higher than Model 1. Validation loss 0.0198, lower than Model 1. Best epoch 83. Use dropout regulation and early stopping. Based on all three criteria, higher accuracy, lower loss, and better epoch efficiency, ANN Model 2 is selected as the best performing model. The deeper architecture with fine-tuned technique allow Model 2 to learn more complex patterns from the weather data while maintaining strong generalization to unseen validation sample. Now let we discuss what we observed from the result. On the data preprocessing, the preprocessing step were absolutely critical to achieving high performance. Without standard scalar normalization, input feature with larger numerical range, such as rainfall, would dominate the ANN training, causing the model to be biased. Proper scaling ensure all four features contribute equally to learning. On model performance, Model 2 superior result confirm that deeper architecture with regularization technique generalized better. The dropout layer prevent overfitting by reducing neuron call dependency, and early stopping ensure training stop at the optimal point. On the confusion metric, the rainy and heavy rain classes show that most confusion between each other. This is expected because these two conditions have very similar meteorological profile, particularly in terms of rainfall amount and humidity. This suggests that adding more features such as atmospheric pressure or visibility could help the model distinguish between these classes more reliably. On the predicted versus actual graph, both models produce prediction that closely follow the actual label, with Model 2 showing slightly tighter alignment, visually confirming its better generalization performance. Despite the strong result, we also acknowledge several limitations of this assignment. First, we only use for input features. In reality, weather is influenced by many more variables, such as atmospheric pressure, cloud coverage, and solar radiation. Including these additional features could improve accuracy further. Second, our dataset has significant class imbalance. The sunny class has 894 records, while cloudy has only 68. This imbalance may cause the model to be less reliable when classifying cloudy weather, since it has far fewer training examples. Third, the date column was not used as a training feature. Weather is often seasonal. For example, certain months tend to be rainier, extracting month, season, or day of year features from the date column could help the model learn this seasonal pattern. Fourth, we only tested two ANN architecture. Other configurations such as deeper network, different activation function, or batch normalization were not explored. Fifth, we did not use a separate test dataset. Our evaluation was based entirely on the validation set, which means we cannot independently verify how the model would perform on completely new, unseen data. Based on our limitation, we have identified 6 suggestions for improving this work in futures. First, add more weather features such as atmospheric pressure, visibility, and cloudiness, which would provide richer input information to the NN. Second, perform features engineering on the data column. Extracting month, season, or day of year information will allow the model to learn seasonal weather pattern. Third, address class imbalance using smooth oversampling or class weighting technique, particularly to improve classification of the minority cloud class. Fourth, applies systematic hyperparameter tuning using grid search or Bayesian optimization to find the optimal combination of learning rate, batch size, and network architecture. Fifth, test more ANN architecture, including deeper MLP, convolutional neural network, or LSTM model, to identify whether a fundamentally different structure could achieve even better results. Six, deploy the train model as a real-time weather prediction application, where user can enter temperature, humidity, rainfall, and wind speed value to get an instant weather class prediction. To conclude the presentation, we successfully designed, trained, fine-tuned, and evaluated two artificial neural network models based on the multi-layer perceptron architecture for weather condition classification. ANN model 2 was selected as the best performing model, achieving a validation accuracy of 99.45 and a validation loss 0.0198, which is higher accuracy and lower loss than model 1. The data preprocessing step, including missing value handling, label encoding, one-hot encoding, then a standard scalar normalization, were critical in achieving the high performance. Proper pre-processing ensure the ANN receive clean, balanced, and appropriately scaled input data. In conclusion, ANN-based models are highly effective and practical tools for weather condition classification tasks. Given proper data preparation and the right network architecture, ANN can help complex meteorological patterns and produce accurate, reliable prediction. Thank you for listening. Now I will pass to Lo Yichan for the demo.
Now let me run a quick demonstration in Google Colab. Before running the notebook, we first make sure our dataset is stored in Google Drive. This is important because Google Colab does not have permanent local storage. Every time the session restarts, local files are lost. By keeping the CSV in Drive, the data is always accessible regardless of the session. Now we are running the coding inside Visual Studio Code, but instead of using a local Python environment, we connect it to Google Colab as the remote kernel. The reason we do this is because we can use Google free cloud computing resources, including more RAM and processing power without needing a powerful laptop to train the ANN. And here, make sure you choose Google Colab, and then here you choose the kernel, and choose Colab. After that, you click on Auto Connect, and then choose Python 3. So that's it. After we finish the configuration, let's try to run the coding. You have to click the Run All button here, and then the Visual Code is trying to mount to your Excel file in Google Drive. As you can see here, we have successfully mounted the Excel file in Google Drive. Now let's have a quick overview before we dive into the detail. So as you can see, the coding running successfully for every step here. And yeah, this is the result that generated, and training, and of course the graph generated, and then the result analysis, and yeah, the last one is the model that has been selected, the best model. Now let's dive into and explain the purpose of the coding step by step. In step 2, we import all necessary library, including pandas and numpy for data handling, scikit-learn for pre-processing, and TensorFlow class for building the ANN. And then for step 3, we load the weather CSV file from Google Drive, which we have completed just now. And then in step 4, we inspect the dataset shape, column name, data type, and statistical summary to understand what we are working with before pre-processing. So step 5 is about the check missing value, and then step 6 is about handle missing value. Pre-processing the data, we try to visualize the data to understand the data that we are dealing with from step number 8 onwards. And you can see the histogram that we visualize. And then in step 12, this is the most important part. We split the data into 70% for training and 30% for validation. The validation set is kept separate so we can evaluate how well the model generalized to unseen data. Then we start to develop the model in step 13 onwards. You can see how we develop, train, and evaluate the two models from step 13 to 18. So this is the evaluation for model 1 and work of model 2, then training for model 2 and evaluation for model 2. Then from step 19 to 21 is about the comparison of both model. Here, accuracy and validation loss for model 1 and 2. Then in step 23, you can see the classification report. It shows the precision recall F1 score for each weather class individually. It gives a more detailed view of performance beyond just accuracy. And then for step 24 and 25 about the confusion metrics, 26 and 27 about the predicted versus actual output for two model. And then lastly, in step 29 and 30, we compile all results into a comparison table and bar chart, giving a clear side-by-side view of both models across all four metrics. And yeah, lastly, our purpose is actually to select the best model, and the code automatically compare both model and select the one with higher accuracy. The output confirm model 2 as the best performing model. Yep, model 2 is the best. Then, so this complete my part of the presentation. Thank you.